Hello, everyone. So I really appreciated all the talks today, and I really liked the talk earlier on avoiding the shiny object syndrome. And so now I'm going to talk to you all about the shiny thing I just made, which I do think is very exciting. So I'm going to talk about explainable AI and how to deal with it in computer vision, and really tackling one of the biggest challenges of that, which is we're all moving, or many of us moving into deep learning and deeper learning and more complex models, and almost all of them have this big black box, the deep representation of many layers with possibly hundreds of millions of parameters that have been learned. And trying to explain that to a subject matter expert, a domain expert, which we've heard said correctly today many times, is absolutely crucial, is very difficult, if not impossible. So you're probably all familiar with, or many of you will be, with saliency maps, or heat maps, or gradient explainers, these kind of splodgy images that you get that show where in an image, an input image, a network has been focusing its attention in order to come to a conclusion, in order to make a prediction. And they're kind of useful, and I'm not saying they're a bad thing. I think you should all be using them if relevant. I use them. I have favorites, but at the end of the day, all they tell you is where in an image is interesting or important to a model. And I want more than that. So I'm going to introduce today Colin. So Colin stands for Counter-Observational Latent Interrogation. I called him Colin first, and then I came up with the acronym. But Colin is a form of counterfactual rendering, which is a term I'm trying to use more and more frequently, which is essentially, counterfactual essentially means what if? What if something else were true? Then what? So I find that this is a very good way of explaining most complex concepts or pieces of information that I want to get across to a subject matter expert. What if this were different? Then what? Is a nice way to start that conversation, is a nice way to start really delving into a big, complicated, context, kind of dependent subject. So my example here is, what if Colin, the goldfish in this case, looked angry? So you can see the top image is a real goldfish. It's an image of a real goldfish. And I've asked a model that understands sentiment analysis from image, what if this goldfish looked angry? And I did this with the new technique that I'm going to walk you through. And what do we see? We see the goldfish slowly but surely getting a snarled lip or a furrowed brow. His fins get kind of puffed out. He puffs out his chest. He shows you what anger looks like, how it gets displayed in an image. But that's not the only thing that I learned from this. I also learned that my model knows all of this. So the model that did this, and it's not photoshopped, I promise you, it really is a model that did this. It knows all of those things. Not only this, and this is the bit that I found very interesting, it got given no images of angry fish. Well, to be fair, I don't know this, because I don't know what an angry fish actually looks like, but I didn't see any images like that at the bottom right in the training set. So what it's using is analogy. It's using its understanding of what humans look like when they're angry and applying it to a fish in a way that it thinks makes sense. And that's quite amazing to me, at least. I find that quite astonishing. So not only does the model know what anger looks like, it can apply it in a context that it's never seen before. And if somebody had told me that, I wouldn't have believed them. But if the model can show me that, now I believe it. I saw this quote very recently, just a couple of days ago, although it was posted in 2020 by Neil Lawrence, the DeepMind guy from well, he's in Cambridge now, isn't he? And he's great. I'm a massive fan. I listen to his podcast a lot and read a lot of his stuff. And his opinion was that AI is kind of stuck in a rut. At least 2 years he thought this, 2 years ago. He thought AI was stuck in a rut because it couldn't communicate to us in a deep enough and rich enough way. And one example of this, he said, was the real danger is that computers don't anthropomorphize. They make decisions in isolation from us without our supervision because they can't communicate truly and deeply with us. Now, Colin looks pretty angry about this. So I think things have moved on. I think actually deep learning is getting into a new realm where we can explain as richly as we can assess and analyze. And I'm going to walk you through two paths, two stories. First, how what I would call counterfactual rendering came about, and then how Colin came about. So to begin with, what I would call counterfactual rendering really started in a technique that many of you will be familiar with, which is activation maximization. So essentially you take your inputs, your image, and you alter it with an optimization algorithm until you get the answer out of the other end of your network that you want. So maybe you want to activate a particular classification. You alter your image until it comes out the other end of your network. And they did this to Google, being they did this to explain what was going on inside the network, because you could activate pretty much any part of the network through this process, and you get some kind of idea at the other end as to what was going on in the network. It was very interesting back when it was done, but now very few people will use this as the way to explain a network because, well, that's what it makes. Top right, you've got psychedelia. You've got, an explosion of too much information to really make sense of. I'd argue this is pareidolia. It's the sort of thing that you get when you look at clouds, you start to see a face, and then your mind fills in the blanks, and you end up seeing a full image of a face when it's not really there. It's got this, but yeah, way too much. So interesting, but not very useful. But I will come back to this. I'd say the next step along the path towards counterfactual rendering is adversarial attacks. I think many of you will have heard of that as well, where essentially you try to alter the image very slightly in order to make a classification change. So picture of pig, how do you alter it very, very slightly, as imperceivably as possible, and then convince a classifier that got it right the first time, that actually now it's an airliner. And this was seen as very concerning, that this meant that AI was very fragile, that it wasn't robust. And it led to lots of very interesting work. And again, it's super cool, but it's not useful in terms of explaining what's going on in the network. It's more about how fragile the network is. I'm going to go about 3 or 4 years later, and that, of course, is an eternity in AI. And all of a sudden, you're getting something very close to what I wanted to achieve coming out of Google again. This time, we're looking at retinal fundus imaging. So this is a picture of the back of the eye. It's totally non-invasive, don't worry. You just get the camera really close, and you take the picture through the pupil, and you get a picture of what's going on in the back of your eye. And what they wanted to do was they had an algorithm that could diagnose various conditions from looking at these photos, and they wanted to make sure that it was using the right features, that it wasn't cheating, it was using sensible, salient features. And so they used StyleGAN, generative adversarial network, to generate the features on the image in order to trigger the classification that they cared about. And it worked really well. Those features, they might not look super impressive to you, but they are very, very convincing as the features that they were trying to generate. So very close to what I was wanting to try and achieve by explaining through counterfactual rendering, showing something to explain what the model knows. And then along came guided stable diffusion. And well, I mean, it's amazing. I don't know if you guys have played with it at all, but essentially, very, very, very realistic images are very easy to generate. And the fact that it is guided, I think, is the real magic. Most of the models that are getting a lot of headlines at the moment are guided via clip or similar joint embeddings, where you can type in some text, and that will guide how a denoising algorithm denoises an image in order to generate a new image. So here we have an example where in that green square, they're going to add noise, and then a denoising algorithm, an algorithm that's learned how to remove noise, removes the noise so that we get a nice picture revealed. But at the same time, it's trying to optimize a vase of flowers. And by doing this, you see a vase of flowers appear magically. Now, this is super close to exactly what I want. For example, under the vase of flowers, you see not just a shadow, but you see a reflection. That wasn't there. And it's understood to do that by looking at the table and knowing that the table's surface is shiny. It knows more than I might have expected about materials, about objects, about reflections, about all kinds of things. And I've learned that from asking it a question. Change this image until it's like something else. Just to hammer home the point, this is an image that, so I've been playing a game with my friends and family on Facebook, and it's simply called Real or Not Real, and I post an image pretty much every day, and they've got to answer, is it real, is it not? This was the first that I posted where every single vote came back real, and it's not. It smashed the Turing test. It was absolutely convincing to everyone. But the thing that really wowed people, the thing that really got people kind of interested in asking lots of questions was, how did I generate it? It was one of the shortest prompts that I gave to the Stable Diffusion Network. It was 2 rocks in love. Now, if I'd asked you before what this was, you probably would have said, it's a big white stone or pebble or rock. But now, everybody says, oh, look, they've got a baby. You've learned a huge amount about what the network knows. It knows analogy. It knows how to make a very realistic image. It knows how to count. But it knows how to also realize that there's 2 rocks that matter in this photo in terms of the context of the text. But there's a big problem. So it sounded like, oh, well, somebody else has solved this problem for me. Explainable AI is already done. I can just ask questions and it gives me the answers, and now I know what's going on in the network. But generative models, the ones I've described anyway, are adding to the problem. You've got one network. Let's say you've got a diagnostic network. You've got a classifier, an image that just looks at an image and gives you a decision as to whether or not somebody's got a particular disease or not, and you want to explain it. In order to use those 2 methods, the GAN and the diffusion network, you're adding more black boxes. Both the diffusion approach and the generative adversarial network approach add not just 1, but 2 or even 3 or even 4 more black boxes to the problem. So what's going on in those? Now you've got to explain more black boxes. So can we do that, but without any more black boxes? All I want is the diagnostic network and to explain it. Everything else needs to be deterministic, maths, or just something I can explain fully. So I did what people often do is I went right back to the beginning. I went back to, do you remember the deep dream, the squirrely psychedelic patterns in the sky approach that happened very early on? I went back to that activation maximization and I just tried lots of things to see what might improve on that, but essentially the same approach. Better regularizers, better optimizers, better models and network architectures and so on. And I started to get something good enough that kept my interest. So you can see here, Colin I'm trying to convert Colin, by the way, to a tiger shark. Reason being that in ImageNet, I think goldfish is number 1 and tiger shark is number 3. They literally were the first things I came to. So I asked the network that could tell the difference between a goldfish and a tiger shark, make Colin into a tiger shark, please. And what I saw on the first run after looking at lots of different options was, okay, Colin's face looks a bit sharky, maybe. I see the swirls and patterns in the background that happened in Deep Dream, but I've managed to tame them a little bit with some of the regularization work. So the first insight that I got, the first thing that I learned from using this very early version of Colin was that the model I used was colorblind. So I just plucked something off the internet and used it and didn't know anything about it, how it had been trained. But I noticed one thing. He was always still orange. It didn't matter how much I optimized him, he was always orange still, and sharks are not orange. So something's wrong there. And I dug in, I did some research and found out that, okay, the models are actually trained with color jitter. So it's colorblind. I've learned something about how the model was trained and what it understands and what it doesn't understand. It doesn't understand color. And then I learned a series of other things. I learned that it is potentially proportionally blind. It didn't seem to alter his silhouette very much. It altered his features, but not his silhouette, so maybe it doesn't really understand distances very well. Maybe this is something else I've learned about the model. I went deeper, as most AI researchers do, and went to EfficientNet B5 and found that the patterning on the side of Colin started to get a little bit more consistent, a little bit more vivid, and I could see spots. Now, this was, I didn't realize at the time, something else I had just learned from Colin. Tiger sharks are spotty, not stripy. I assumed they would be stripy. So deeper is better in some ways. We start to see more texture, more fidelity in the details that it generates when it's counterfactually explaining things. So I like efficient nets now, and I'm sticking to B5s usually. But I looked at smaller networks just in case, and actually, VGG16, EfficientNet B1, much smaller networks, much simpler networks, actually got sort of decent-ish results. Again, this is very early stages of Colin, so don't worry, it gets better. But it did get worse. I looked at efficient nets, and they were terrible. I got almost no improvement from looking at Colin through, looking at this image through the Colin system. We think we know why this is, but we don't know. We're still looking into it. One of the reasons we think this might happen is efficient nets have efficient blocks split into at least 3 different convolution layers which have different resolutions. And if they've got different resolutions and then they get combined further up the chain, well, how do you know which pixel actually made the activation that ended up going further up the chain? A little bit technical, but we think that might be the case. We're still looking into it. But the point is, it got us looking, it got us thinking, it got us into the idea of selecting a model architecture based on how explainable it is. So, what if we can improve on all of this using the lessons learned from diffusion models, which are amazing, produced 2 rocks in love? And the answer is yes, you can. So this was the very first example of applying it in a kind of medical task. And we wanted to understand why one of our models, excuse me, could understand, or that could predict the risk of chronic kidney disease from looking at retinas. That might not be obvious, right? You're looking at somebody's eye and you're trying to figure out whether their kidneys are healthy. Why would that be? How does our model work? So we asked Colin, and using the new additions of what we'd learned from diffusion models, but not adding a new black box, we got these images. These images are far more useful to us. We can see that the vasculature in the top right, you can see the output as a video. It's a sort of slow-moving video, I'm afraid. The vasculature, the veins, are shrinking tip to root. They're getting shorter and shorter. And this is, if you ask a medical expert, reasonable. They say, yes, that may well happen. We also see microaneurysms and mottling, which is associated with hypertension and aging, both of which would correlate with chronic kidney disease. So we're seeing sensible features. We're seeing things that make sense. And it gives us more confidence that the model is doing what it does using sensible signals. We looked at pathology, same thing. We found that it could generate very realistic counterfactual renderings. So you've got two real images at the top. You've got a real sclerotic, not healthy image at the bottom and bottom left. And on the bottom right, you've got the counterfactual rendering of sclerosis, but of the top right. So that one is synthetic, bottom right. So it works across lots of different domains. Next, we looked at eczema or atopic dermatitis. And we got a relatively healthy input. And we said, OK, make this way worse. Make it so somebody's got really itchy rash. And not only did it put the rash where we thought it should, it did it in ways that made medical sense. You got the little spots on the palm of the hand. You got the worst rashes that got the most scratches at the joints, and so on. So again, it's making medical sense, so we're more confident that the model's doing its thing sensibly. It did this. One of the useful things about this is you can give it one input and then ask it for lots of answers. So, and every time it'll give you new examples of what's wrong with the patient, potentially, if they have the condition. So you can just keep running it, learning more stuff. This is one of the cases where, and again, so just to make it clear, eczema is not very nice, but it's not fatal. So I hope you don't mind seeing these. The healthy example on the left gets re-rendered by two different models, one of which had labels that were made from a process that cares about scratches, that the doctor is asked, label the severity of this condition, and you're allowed to count scratches as a significant indicator of severity. And on the far right, they're not allowed to do that. So this is the labels that we're generating, right? Now, when we train the algorithm, and then we use Colin, and we say, OK, show us what eczema looks like, this one only really added scratches and redness. And that one had a way more interesting interpretation of what eczema was. It knew about dry skin and spots, and it got a way more deep understanding. So we chose, not only did we choose that model, but we chose this way of labeling the condition. So it's getting a lot of use. Bear in mind, this technique came about 5 months ago. And this one is my favorite by far. Wilson's disease is a condition where copper will build up in the body. The liver is not metabolizing it correctly. It builds up in places it shouldn't be. It gets very bad. And there are treatments, which is good. But you need to diagnose it in order to start treating. So we made a classifier. Now, A is a real example of somebody with Wilson's disease. And you can see a kind of milky ring around the edge of the iris. And that is copper building up in the eye. So you can physically see it. You can look at the person and see that it's there. So that's A, top left. B is a healthy eye. There's no copper there. And I want to train an algorithm. Now, problem is, Wilson's disease is a rare condition. If you scour the world, you're going to get 24 examples. And you want to make a tool that can diagnose clinically and safely with 24 positive examples. That is very dangerous, right? You don't want to do that willy-nilly. You don't want to do that without considering things first. So we put it through Colin, and we got a bunch of algorithms that did this, and one that did this. So in C, we ran a whole bunch of training and saw a bunch of models, all of which supposedly got really good results. And I don't know if you can see it from there, but essentially in C, it's generated JPEG artifacts. It's picked up on the fact that all of the positive examples we got, we took from the internet, because that was the only place they were, and they were all low-quality JPEGs. All the negative examples that we put into our model were all high-quality PNGs. So we could see with our own eyes, when we saw C coming out of Colin, that don't use that model. You've made a JPEG detector. You've not made a Wilson's disease diagnostic tool. So, but D we found very interesting. One, because it didn't do that. And two, because, I'll show you, there's some arrows. Two, because it didn't do what we expected. What it showed us was, it's not an addition of information that indicates whether or not somebody has Wilson's disease according to the model that worked. It's actually the occlusion of information. All of our irises have a pattern around the edge of them, but the copper hides that. So it's actually blurred out the pattern that's normally there. And that was the feature that it decided to use. Now that is actually better than the one we came up with. The feature that we were expecting was you're going to see a green ring around the eye or some darkening or something. But then when we looked at the data more, copper presents itself very differently in lots of different ways in everybody that has the condition. Sometimes it's bright, sometimes it's dark, sometimes it's brown, sometimes it's green. So adding a color to the iris would not be robust. The algorithm instead removed the feature that was actually there. If you look in B, you've got this ring around the iris. That's real, that's healthy. And in D, it's gone. That occlusion of information is actually a really good feature to pick up on. So what did we learn? We learned that occlusion of pattern is a stronger indication of Wilson's disease than our assumptions going in. This is a reasonable signal to use. Performance is good despite being colorblind, possibly because of it. And none of this would have been determinable using any of the other methods that we would normally reach for. Things like SHAP gradient explainers and so on, which, like I say, are really cool. You should use them. So what's the trick? So I wanted to do better than this on this slide, so sorry if it's not super clear, but essentially, we add noise to the image. And whilst we're adding noise, we're also optimizing toward the class that we want to activate. And whilst we're doing that, yes, you can see sort of reddening and splodges and things appearing. But then we turn around again. We go in the other direction. We stop adding blur, and we keep optimizing, and we start re-merging with the original image. So it's a bit like Stable Diffusion, but no other black boxes. Nothing needed to be learnt. There's only the diagnostic model at play here. So everything you see that's being shown is explaining only the diagnostic model, not the generator. So what did we learn in general? I think common deep learning classifiers are not perceiving the world as we assume they are. And that's super important to know and understand and accept. Some network architectures are more conducive to explainability than others. And diffusion is a really cool, shiny thing. And I absolutely suggest everybody have a play with it. And does does not, I think I've gone wrong there. Yes, Colin does not use additional latent space. We know this. It's fast. It's very quick. It's under a second. So you're not training anything. You're not training some new big generator model. But to run this takes less than a second. It retains the essence of the diversity of the original image. So this is super interesting if you're into the idea of using synthetic data to augment your training set. You can take a huge number of healthy eyes from the internet or from a sensible and responsible source, and you can alter it, some of it, half of it, to look like it has Wilson's disease, and now your positive set has a massive diversity. Now it's far more robust. And rather than it being fully synthetic, it's semi-synthetic. It's got all the diversity of the real data that you used as a donor image, but it has the signal of the positive traits. So finally, some bits of the puzzle that we're still working on. Momentum seems key to this, but it's very difficult to figure out exactly how to calibrate it. So we want to figure out that. Fast AI are looking into this. And the mixing ratios, how specific or literal do you want to be versus how poetic do you want to be? Do you want two rocks in love, or do you want this eye has Wilson's disease? And I'd say being able to control that is super powerful, and possibly the next big thing to look into. And just to be sure that generative models really are quite fascinating and illustrative, almost every image in this slide deck was generated by AI, including everything you see on here, apart from our logo. And that's it. Thank you for listening. Any questions? Yep. Yep.
I would like to know about this synthetic image that you generate out of the good case scenario. How can you evaluate how good is for training your model with these images? I guess it's like an intensive work with doctors, and how can you develop a little bit more on that topic?
This is a really good point. So yeah, how safe is it if you're using synthetic or semi-synthetic data, and how can you be sure of the performance of the metrics if it's not real data? We always use real data for the metrics. So every test set is fully real. And yes, we train on synthetic potentially, depends if it suits the task at hand, but we never try and give evidence to a model working correctly by using synthetic data, because no, that would not be safe. Yeah.
I was just wondering what your workflow is for evaluating how well the prompts explain, the generated images explain what your model's learned. Do you show lots of them to experts and say, is this what you expected to see? Is there any way to quantify it?
So this is a good point, but it actually prompts me to clarify something. So the prompt way of working is stable diffusion. It's a different thing. We learned from that in order to make Colin. Colin doesn't take text prompts. It takes a model that we've trained in a fairly standard traditional way to usually classify, but sometimes do regression. And we are activating the class that we care to explain. So we don't actually give it text prompts. We give it, we want to see what does Wilson's disease look like, for example.
And then, so when you do that, so what does Wilson's disease look like? Is your validation to simply show that to domain experts and get their opinion?
Yes, and we find that that's far easier to show to somebody and have a good conversation about. So yeah, if I try and explain what's going on in the network in any other way, I just get blank looks usually. But if you show them images and say, look, this is what the model thinks this condition looks like. It might not look exactly like the condition, but it shows you what it's going by, what's going on in its head when it makes that decision. That's a much easier conversation. And yes, exactly. That's the purpose of it, is to get in front of those subject matter experts and talk their language. Yeah, at the back.
Hi, thank you. Really interesting talk. You mentioned about the hidden biases that those other type of models may include when you put more black boxes inside. However, a big critique of these generative models is the biases that are included in the data sets used for training the models in the first place. How do you envision, how is this influencing the explanations that you're trying to obtain from here? And what do you believe would be a feasible way to address this type of biases in the data itself that is built to train the models that you are relying on?
Yeah, that's a really good question. So this is one of the big strengths of this approach is there is no generator. There's no generator model, so it doesn't have any biases because it doesn't exist. We don't add another generator to it. But it does allow us to then construct a training set that is representative of the profile that we care about, the population profile that we care about. And usually that's way more diverse than the data we have that's labeled. So like in Wilson's disease, we have very, very few examples. Definitely there are entire, a lot of demographics are simply missing entirely from the data. And so being able to take the data from those demographics, make them look like they've got Wilson's disease, and then train again, retrain the model, but test only on real data. Then you've got the best of all worlds. You've got the diversity that you want, but you've got the test that is valid and reliable.
Yeah, great talk. I was wondering, the point you made at the end regarding the ratio, the balance between the blurring between, like, is it Wilson's disease or is it something else? Can you elaborate on more in terms of how you're implementing that balance? Is it some sort of energy function or?
So the details will be published and we'll also be open sourcing the product. We aim to open source it by February. It might get delayed. It's most likely to be delayed because we want to publish as well, and that often adds delay. So those sorts of details will get better explained in there. But essentially, yes, you can use stable diffusion, which is, like I say, as poetic as you like, creative as you like. Or you could use the raw Colin and be very, very specific. Blending between the two is relatively easy. Essentially, you just you decide what proportion you blend towards in the next iteration. It's simple as that. So it's just a knob you can turn in order to make that blending. Bit of a hand-wavy explanation, but yeah, the details will come in full soon, hopefully. I saw a couple more. Lars.
I have two questions actually. First one,
Thanks. Did you try this technique on a problem where you didn't get good results to explain why you didn't get good results and potentially improve them?
So not yet. We definitely get cases where we have to play with the dials a little bit more. So momentum, for example, changing the momentum in order to get the best possible results is an example where, yeah, if we hadn't done that, then we might have come away thinking it wasn't a good result. But so far, every task we've found pretty quickly a way of illustrating what the model thinks. So yeah, so far so good. Sorry. Yes.
So one more. So you might use the technique to create synthetic data, and you train on that, and then you say, of course, you just test on real data, but you might not have in the test set any images from a certain demographics that you now are trained on. Yeah. So is there any way to get any statistical certainty that the model performs well in those cases?
The only way to get real data is get real data. So yeah, which is something we're doing. Yeah, we are going out there and collecting actively as much data as we possibly can. And yeah, I'm involved with that project at the moment. But at the end of the day, it's a rare disease. And so you could get everybody's data in the world who has Wilson's disease, and it would still be a small data set. So we can only do what we can do.
Thanks, it was really interesting talk. I was wondering, when you do synthetic data and you merge it with your real data for training, so what's the ratio, especially when it comes to pathology data?
So it would very much depend on the situation at hand, not just the task, but the quality of the data you've got, and the imbalance that you've already got, and what task you're trying to solve. So yeah, I mean it varies. Sorry, there's no perfect ratio as far as I can tell. Some things are obviously more difficult than others to solve. So yeah. You probably need more data for those.
Can it get more than your real data?
Sorry?
Can you get synthetic data more than your real data? Or no, you still have to?
So you can use entirely synthetic data or semi-synthetic data, so data that's part real and part generated, altered, entirely in the training. Only that, and you get good results. And then only use real data in the test set. But of course, you have to use some test data to make your model that can create the synthetic artifacts. So you still got to be very careful you don't pollute your test set with training data and so on. All of that gets a bit complicated when you've only got half a dozen positives. But it's possible and yeah, helps generally.